Hello, everybody, and welcome to my talk on accelerating SARS-CoV-2 low-frequency variant calling for ultra-deep sequencing datasets. My name is Bryce Kille from the Treangen lab. This work was sponsored by the C3A Grant Challenge. Just a talk outline before we get started. We will cover some of the motivation for what our goals were with the project, some background on variant calling. We'll describe the low-freq algorithm as well as our contribution. We'll then jump to the results, and then we'll talk about our conclusions from our study. So as far as tracking outbreak variants, being able to classify or identify variants has been a long-standing problem in bioinformatics, but more recently, the problem has been related to being able to track variants for outbreak studies. For example, we see on the right here, this is the frequency of the D614G variant in SARS-CoV-2. We can see that it started as a very low population frequency, and within a couple months, it nearly shot up to 100% of the population. And being able to identify these variants can assist researchers in reproducing evolutionary history as well as tracking the viral transmission. And in this case, for D614G, evidence has shown that it actually increases the infectivity. So our hope is by being able to identify these variants earlier, we might be able to have a head start on kind of characterizing the variants as well. Excuse me. So as far as the data goes for being able to identify these variants, on the right here we have essentially the number of genomes in the top right on the y-axis, and then the month on the x for 2020. And we can see quickly the number of genomes in NCBI, or in GSED grows with each month. And this is just last year. So we saw at the end of last year, roughly, there was over 200,000 genomes in the GSED database. And for other outbreak studies for viral genomes, there have been upwards of tens of thousands. So we can see quickly here, the size of the data set outpaced other viral transmission studies or data sets. And the size of that data set at the end of 2020 amounted to 10 terabytes. Now, as of May 2021, there's actually over 500,000 SRA runs for SARS-CoV-2 and NCBI, and actually over 1 million in GSED. And that amounts to actually over 35 terabytes in NCBI, just for the 500,000 SRA runs. So our project goals were actually to be able to comb through all 35 terabytes of those SRA runs and basically scale up variant analysis pipelines or even studies and tools to be able to facilitate global surveillance of all the variants. So with those variants, we would attempt to build basically a database of all the variants so we could keep track of them and try to perform some studies and be able to share that with other researchers around the world. And to facilitate all of that, one thing we set out to do was to improve the low-freq variant caller algorithm to speed up computation on these deep sequencing runs. So the low-freq algorithm was developed in 2012. It's a very popular tool for sensitive identification of variants, has over 600 citations. Our recent benchmarking study from 2017 compared it to other tools for variant calling and found that they had comparable performance with very good sensitivity, and that was definitely our attraction to it. One issue with low-freq, though, is its runtime. We see on the top right actually a figure showing the table of low-freq's runtime compared to other tools, and we notice that it is significantly longer than some of the other tools here. And in fact, running low-freq on all 500,000 of the data sets in NCBI would take actually over 20 million CPU hours. And so that was one of the reasons we want to speed it up, is because any fraction of time we can save on 20 million CPU hours would save a significant amount of resources. And so first we'll cover actually how we get to this type of variant calling and kind of the pipeline required to get there. So in NCBI, we have basically the read sets. And so we start with a set of reads. And for each one of these reads, for each base pair within a read, we actually have a quality score of the base pair read or the base pair call. And that quality score gives you an idea of how confident the caller is that that is the correct base score. It's basically an error probability or a score that you can infer the error probability from. So with these reads and their quality scores, we map them back to the reference genome. So These are reads from SARS-CoV-2. We map them back to the reference SARS-CoV-2 genome. And so now then, for each position, we have a set of reads mapped to that position, or a set of base pairs mapped to that position, as well as their quality scores. And the core question for all variant callers is, how can you infer variance given this information? So for a single column, the reads mapped to that column, and the quality scores for those base pairs, how can you infer a variant? So we'll jump into how LowFreq does this. So essentially, LowFreq treats each base pair column as a sample from the binomial distribution. So to give a quick example, if we have a reference base and k columns to a non-reference base variant, what's the probability of getting at least k errors in all of the reads for that column given their Phred scores? So essentially, we're asking what's the probability of getting more than k errors if the probability of an error for each read is given by the Phred score. And this ends up being the Poisson binomial distribution, where each of the independent samples is a Bernoulli trial with its own independent and not necessarily identical probability. So that's the key here, is that the probabilities are not identical. And to be able to calculate this distribution, we have a naive formula on the right. So essentially, f sub k here is actually all of the subsets of size k. And quickly we see that obtaining all the subsets of size k is exponential time complexity. So we quickly jump to something a little bit more reasonable. And this here is O of nk dynamic programming complexity, where n is the number of reads for a column and k is the number of variants. And it's worth noting that the number of variants for a column is actually O of n, since it could be the case that half the reads in the column are variants, or even a quarter, or even in some cases the entire column is all variant. And so this ends up kind of growing substantially as well once we get to much deeper sequencing data sets. So we'll run through an example of how LowFreq works. So this is a column for LowFreq here, and this is the reference base G. And we have here that the non-reference base, or the variant, is C. And these are just some examples of the error, or the quality scores in conversion to error probabilities. So we actually have this formula for converting the quality score to the error probability over here. And so then with this information, we need to infer whether or not there's a variant present. And so what we have here is just a classic hypothesis test, where we have that the null hypothesis is that we saw k of the deviant basis, or we saw the k variant just purely due to chance given the error probabilities. And the alternative hypothesis is that there's actually an underlying variant that caused those base pairs to be called. So we can do this by essentially computing the survival function of the Poisson binomial distribution for everything greater than k. And in this column, we get an example where the p-value is 0.01, which means we can likely reject the null hypothesis and assume that there actually is a variant present in this column. And just another example, we can see that there's cases where it's actually all the reference base, and we can be fairly confident there that there's actually no variance present. The third case, of course, is when it falls somewhere in between the two extremes. In this case, we don't call a variant, but we do notice that there is a bit more evidence than before, when there was no variance present at all. So we quickly jumped into some benchmarking of LowFreq, and we noticed right away that most of the time was actually spent calculating this Poisson binomial distribution. In fact, in a sample with 20,000 coverage on average, we noticed that it was spending around 80% of the time computing this exact p-value for the Poisson binomial distribution. And even more interestingly, these p-values actually usually fall to either of the extremes, either nearly 1 or nearly 0. So in some cases, 10 to the negative 7th or smaller, but essentially never near the significance threshold of 0.05. And so that kind of led us down to this path of believing that it's not necessary to calculate the exact p-value in most situations, as long as we have an approximate idea of which one of these extremes it falls at. So here are some examples of Poisson approximation formulas. We have essentially the parameters here on the right, where the mean is just the sum of the p-values, and then some of the more complex parameters, such as the standard deviation, the variance. But fortunately for our approximation, we actually only just need the mean. So we use the Poisson approximation, the Poisson binomial from HiCOMB in 1960, but it's worth noting that there's actually a couple of other approximations as well. And there's actually even other studies that use these approximations, the Poisson binomial. In fact, recently in a Nature Genetics article, they use a Poisson binomial distribution to actually model the number of mutations seen in regulatory elements for cancer patients. So this slide just gives an example of the performance of the approximations. So it's worth noting that the performance of the approximations depends on the underlying distribution of the p-values. So in this case, if we set this p-value distribution to this beta distribution, we'll get the performance on the right. But it's worth noting that these performance behaviors or patterns won't necessarily hold if this distribution of underlying p-values changes. But we can get an idea. So here on the right, we see the different values of n, so the different sample size, and the performance of the approximation. And given that our n, or our number of reads for a column, is significantly large for our cases, generally over 1,000, we can see that the Poisson approximation falls fairly closely in line with the exact, which is marked by the black line, the DFTCF. Excuse me. So how we use this approximation is we first compute the approximate Poisson binomial p-value, which we'll denote here as p hat. And with this approximate value, we essentially want to determine whether or not it falls significantly above the threshold. So in the case that the p hat, or the approximate p-value, falls significantly above the threshold, we can be confident that the exact value would not fall below the threshold, and so we don't call a variant. And we add this 0.01 here, which is actually something that we let the user modify as well in the source code as an argument. But this value here essentially allows for some error in the approximation. The alternative is that the approximate p-value falls below that significance threshold, in which case we fall back to the original low-freq algorithm to be able to determine whether or not there's a variant, and if there is a variant, what exactly the p-value was for that variant call. So with this speed up to the low-freq algorithm, we actually notice some pretty significant speed ups. In fact, on the larger data sets, we get nearly up to a 5x speed up on read sets with hundreds of thousands of reads per column. And this ends up saving hundreds of hours in some cases for the large data sets. But it's also worth noting that on the small data sets, we actually don't notice a speed up. And one thing that has been brought up is the fact that even though in our cases there were actually no variants that were missed, so we had no false positives, no false negatives, it is technically or theoretically possible for this shortcutting to introduce false negatives when the approximate p-value falls significantly above the threshold, even though the exact p-value would fall below the threshold. And that's something we aim to fix in the future. Excuse me. But the main result here is that with these speedups, we're able to save tens of millions of CPU hours by just improving the existing low-freq software. So a couple future directions. The first one is actually just to implement an early stopping criteria in calculating the mean column p-value. And so that's essentially to compute the parameter, the mean for the Poisson approximation. And that requires us to sum over every single p-value for every single column. And it's worth noting that the actual original low-freq algorithm has some shortcuts that don't require it to go through every single element for every single column and allows it to stop at place in time. So we believe that this actually might be one of the reasons that on smaller data sets, the Poisson approximation actually performs the same as the Poisson binomial exact calculation. And so that's one of our future goals, is to make sure that this speed up holds across all data set sizes. The second future goal is actually to find an approximation method that, we can be guaranteed as a bias estimator. And the reason we want a bias estimator is because if we can be confident that the estimator is, let's say, an underestimator of the p-value, and yet it still falls above the significance threshold, then given the bias of the estimator, we can actually be even more confident that the exact value would fall even higher, which means that we'd have more confidence that the p-value would be even further above the threshold. And essentially the underlying goal here is just to provide some sort of theoretical guarantee or theoretical confidence that this approximation isn't introducing any false negatives. Because I think that one of the biggest contributions here is we want to make sure that users will only notice a speed up and not necessarily any result changes. That's it for our presentation. I'd like to thank the entire team of Covariance, Professor Nancy Amato, the PI for the team from UIUC, Professor Lawrence Rauchwerger from UIUC as well, Professor Todd Treangen, my PI and the co-I for this project from Rice. I'd like to thank Dr. Michael Nute, the postdoc for our lab at Rice University, I'd like to thank my classmates, Nicolae Sapoval and Yunxi, 2 PhD students from Rice University, and then the PhD students from UIC as well, Elliot Robson and Nathaniel Asefa. I'd like to thank the HiCOMB reviewers for all their feedback. I'd like to thank Mehmet Koyuturk and the rest of the HiCOMB committee. And then, of course, I'd like to send a special thanks to the original developers of Lowfreak, Andreas Wilm and Niranjan Nagarajan, for all their help and guidance. And also, very importantly, letting us merge our changes back to the original source code for Lowfreak. They were very helpful throughout the entire process, and it was really great to contribute to open source software. They really helped us through that. And then, of course, I'd like to thank C3AI for all of their funding support. Thank you for coming to my talk.